Okay, so what I want to do now is finish up annuities. So let's talk about annuities in perpetuity where payments increase geometrically. So remember, if we have an annuity immediate where payments increase geometrically, then the present value is given by this formula. So here, N is the number of payment periods, J is the per period interest rate, P is the first payment, and each subsequent payment increases by 100 times R. So at the end of the first period, we have a payment of P. At the end of the second period, we have a payment of P times 1 plus R. At the end of the third period, we have a payment of P times 1 plus R squared, and we keep going for N periods. So we can look at what happens when we just keep doing this indefinitely, which is the same thing as saying the number of payment periods goes to infinity. And as long as R is less than J, so that what I have this quantity here, where my cursor is going to be less than 1. It's going to be strictly between 0 and 1. So that when we let N go to infinity, that's going to be 0. So we just get the formula, the present value of this annuity immediate in perpetuity, where the payments increase by 100 times R% each period, is P over J minus R. Now, if R is bigger or equal to J, then really this annuity doesn't really make much sense, because what's going on is, when you have payments way out in the future and then you take the present value, normally, that kind of payment way out in the future is basically worthless now, thanks to inflation, or not so much inflation, but thanks to just discounting by a whole lot of years. But because these payments increase, each period so rapidly that when you take the present value, it's not, if you take the present value of payment way out in the future, it's not necessarily worthless. And in fact, when you do that and add up all these present values, you just get something that's infinite. Whereas when R is less than J, even though payments are increasing by 100 times R each period, we have interest is bigger than this R, so the effect of discounting counteracts the increasing nature of the periods, so that you actually do get a finite number when you add up the present value of all these payments. Now that didn't quite make sense. It's not a huge deal, though it really should make sense. What's important is just to understand this formula. And I'll do an example in a moment. And we won't really need a formula for an annuity due in this situation. You could just multiply this whole thing here by 1 plus J. So it would be P times 1 plus J over J minus R. But it's really not needed. Okay, so let's put this to good use. And let's do something very similar to a former exam FM problem. It's very similar to 2.3.4 in Broverman's Mathematics of Investment and Credit. So we have an annuity immediate in perpetuity that pays $1,000 for the first 10 years. Excuse me. And then every year thereafter increases by 2%. Let's find the present value if effective annual interest is 3%. Okay, so what I want to do is draw the time diagram. That's very helpful here. Okay, so, right, so for the first 10 years, it's just $1,000, nothing special here. And every year thereafter, I'll just write 2 of them, it increases by 2%. So next, at the end of the 10th year, it's going to be 1,000 times 1.0. Sorry, at the end of the 11th year, it's not the end of the 10th year. At the end of the 11th year, it's 1,000 times 1.02. 1,000 increases by 2%. At the end of the 12th year, it's 1,000, 1.02 squared. Whatever this is, increases by 2%. And you keep going. Okay. So what I want to do, and you don't have to do it this way, I'll explain this in a second. What I want to do is break this up into 2 annuities. You definitely have to break it up into 2 annuities, but I want to break it up into these 2 annuities here. The first is a 9-year annuity immediate. Okay, and then the next is going to be an annuity in perpetuity that starts, the payment periods start at the beginning of the 9th year. So it's an annuity in perpetuity, that's an annuity immediate. Okay? And the logic here, the reason why I'm doing it is the annuity in perpetuity will start with payments of 1,000 and increase by 2%. I'll do it a slightly different way in a second, well, after I finish this. So let me first just do this here. So the first annuity, yeah, nothing too strange here. It's a 9-year annuity. Payments are $1,000. So the present value is just 1,000. A 9.03, 3% interest per period. And this is going to be, plop this into the calculator real quick. So 1,000 payment. Again, as I said a million times, order doesn't matter. So 9N, 3, IY, compute present value. And this is 7786.11. Okay, so right, this is the present value of this annuity here that I circled in red. So let's do the blue annuity. All right. Okay, so we still want the present value, at the beginning of this entire annuity. So we want the present value at t equals 0. Okay. Okay, so right, 1,000 at year 10. We're at the end of the 10th year, at the end of the 11th year. 1,000, 1.02. At the end of the 12th year, make this a little neater. Sorry about that. Let's not get rid of that whole thing. Guess there's no way not to do that anyway. All right, sorry about that. Right, 1,000, 1.02, 1,000, 1.02 squared, this, etc., etc. Okay, so right, so the way we have it set up, we can just plug and chug into our annuity immediate in perpetuity formula, where payments increase by 2% each period. So P is 1,000. Okay. J is just the per year interest rate, 3%. Payments increase by 2% each year. That's all we need to plug into our formula. So it's 1,000 over our J minus R. So, sorry, that's 0.02. So it's obviously 100,000. Okay, so, but we need to discount this by 9 years. That's 100,000, 1.03 to the minus 9. And that's going to give me, let's see what that gives me. So I'll do 1.09 first. 1.03 to the minus 9. 1.03 to the 9 minus times 100,000. And we get 76, 641 to 7. I'll just rewrite the 7 here. Sorry about that. And 67 cents. 76, 641, and 67 cents. Okay, right, and that is the present value of the blue annuity at t equals 0. Okay, so, right, so I just add up the two present values. So total present value, 778611 plus 84427. Sorry, that's the answer. Yeah, 76, 641, and you get 84427 and 78 cents. Okay, so right, so what I want to do is redo this problem, but let's instead, I'll do this a lot more quickly. Let's instead do a 10-year annuity with these level payments, and then do a annuity in perpetuity where the payment periods start at the beginning of the 11th year, where P is 1,000 times 1.02, which is 1020. Let's just double check that we get the same answer. Okay, so right, let me just erase this, erase that, erase this here. So otherwise it's the same. 10, 10. Okay, so, and like I said before, I mean, I'm just going to re-enter this. It'll take a second. 1,000 payment, 10, and 3 interest, compute, present value, slightly larger. With 8530 and 20 cents. Okay, so let's go here. So right, so let me get rid of this here. Get rid of all this here. Okay, so we've taken care of the payment at the end of the 9th year. Or rather, we've taken care of, well, that we have. We've taken care of the payment also at the end of the 10th year. So let me get rid of this. I don't think I can erase. Oh, I can. There we go. Okay. Right. So let's find the present value here. It's 1,000, 1,020, 1.02 over same thing, 0.03 minus 0.02. So let's see what that is. 1020 over 0.01. Well, it's just 102,000. Okay. So discount this by 10 years. Okay. So take this times 1.03 to the 10 minus. So 58,897. What did I say? This thing would stay here. 75,897. And 58 cents. Okay, so this is the blue. Yeah, let's just check that it doesn't matter, that we get the same answer. Okay. Right, so 8,530 and 20 cents. So let me write that down. Okay, and let me write down the other one, 75,897, 58. So let's just check, add the two up. Okay. So total present value, doing this problem a little differently. 8,530.20 plus 75,897.58. 7.58. See what that adds up to. Well, let's just take this plus 8,5. .20. I don't know what I did wrong, but anyway, just 1 second. I'll just re-enter it, 8,530. .2 plus 75, 897, 58. And we get the same answer. 884, 427, and 78 cents. Okay, so it checks out. So it's really, I mean, it's good to understand both ways. I mean, I don't have a preference really. I've had people do it either way on quizzes and exams. Either way is fine. Bother me whichever way you do it. All right, so let's talk about one last topic for annuities, and that is an arithmetically increasing annuity immediate in perpetuity. So let's suppose we have payments of P, 2P, 3P, 4P, et cetera, at the end of each period. The effective per period interest rate, as usual, is J. then let's look at what the present value is. So if we basically have this annuity that I described a second ago, and we stop after n periods, so at the end of the first year, at the end of the first period, it's P. At the end of the second period, it's 2P. At the end of the third period, it's P, et cetera, et cetera, et cetera. At the end of the nth period, it's NP. Then we have this formula here, IANJ. So all we're doing is letting n go to infinity. These payments keep going and going and going. Okay, so right, if we assume that J is positive, as we are, I mean, J negative means a contraction, and that does happen, you know, we're taking more of, like, let's say, if we're taking a long-term perspective, in the long term, you know, there is, you know, growth does occur. So we're assuming J is positive. And remember what nu is. It's 1 over 1 plus J. So nu is strictly between 0 and 1. And you should remember or use L'Hopital's rule to get that n nu to the n, because nu is between 0 and 1 strictly, this is going to go to 0. So the nu to the n goes much faster to 0 than does the n. So the nu to the n wins and forces the whole thing to go to 0. Okay, and we have a formula for a infinity j. So this is basically like a infinity j double dot minus 0 over j. So we just plug in, this is 1 plus 1 over j. So divide everything by j, it's 1 over j plus 1 over j squared. Okay, and I should mention that it doesn't really make sense to have a arithmetically decreasing annuity in perpetuity, because what's the setup there? Well, you start off with NP, and then you go to n minus 1p and keep going until you hit P. So just by the setup, you start, you know, it only makes sense for an n period annuity. You're going to eventually deplete the account. So yeah, so it just doesn't make sense, and you really won't need to take the present value of an annuity due that's arithmetically increasing in perpetuity, though. As always, you can just multiply by 1 plus j here to get the present value of an annuity due that increases arithmetically in perpetuity. Just like anytime you want to go from a formula involving annuity immediate to an annuity due, you just take your annuity immediate formula and multiply by 1 plus j, because annuity dues are the same as annuity immediates, except for present value purposes, for an annuity due, you're discounting everything by 1 less period. Yeah, so let's do another example similar to 3.11 in Broverman's book. And that's going to be similar to homework I'll assign. So a perpetuity immediate, an annuity in perpetuity, is purchased with payments starting off at 15, increasing by 5 each year. A perpetuity due is also purchased with annual payments of 100. And that just means it's an annuity in perpetuity. If they have the same present value, find the effective annual interest rate. Okay, so this is a bit convoluted, maybe not so realistic, but anyway, it's like the previous example. It definitely tests if you understand what's going on, so it's not a bad problem, really. Okay, so let's draw the time diagram for the first annuity. So you got to be a little careful with this. So at the end of the first year, it's, at the end of the first period, it's 50. End of the second period, it's 55. They all increase by $5, starting at 50, so 60 at the end of the third period, etc., etc. So this is not of the form P, 2P, 3P, etc., but we can get it into the form, to basically get to that form very easily. So each of these payments increase by $5. So what we're going to do, what works to basically get it into that form, essentially, kind of, is we're going to write this as, well, because it's $5, we're going to write it as 45 plus 5. Again, because I'm doing this because each subsequent payment is $5 more than the previous one. So what does that mean? Well, let's write this as 45 plus 10, 45 plus 15, etc., etc. And really just this trick works where you just basically take the first payment, subtract 5, and I'm subtracting 5 because each subsequent payment increases by $5. And then write the rest of the payments as 45 plus something. So obviously this is 10 is 2 times 5. Okay, so right, so I'll write that 2 times 5. And obviously 15 is 3 times 5, and this trick will always work. So now we can write this as the sum of two annuities. One is just an ordinary annuity in perpetuity, and the other one is an annuity with starting off with P equals 5 and increasing, it's 5, 2 times 5, 3 times 5, etc., etc. So really no need for a timeline. So for the red one here, it's just simply, well, it's just 45. And this is at t equals 0, but that's kind of obvious. So it's 45a infinity. We don't know what I is. So I just double check something real quick. Go back here. So it is actually annual payments. I was saying per period. It is annual payments. Anyway, so right, we don't know what I is, but that's okay. So this is just going to be 45 over I. Right. Okay, let's get the blue. This is going to be, well, we just had the formula a second ago. It's going to be, my P is 5, so it's 5. Sorry, it's 5 over I. 5 times 1 over I plus 1 over I squared. Okay, and again, this is my P here. It's P, 2P, 3P, etc., etc. Okay, so going to the next one. Well, there's really not much to it. The next one, we're given that it is just a perpetuity due with annual payments of 100. So we just plug and chug into the formula for that. Don't need to really draw a time diagram. So the second annuity PV is going to be, well, it's just, sorry, so it was 100, 100A infinity, double dots, immediate due. I actually want to find out if this is really double dot or if it's actually kind of umlaut, but anyway, whatever. And the formula is 1 plus 1 over I. So it's just 100 plus I. And maybe go back a second. So, right, so using the same language here, the first annuity total. Well, we just add these two up, and that's 45 over I plus 5 over I. Last time I checked would be 50 over I plus 5 over I squared. So these two present values we're given are equal. And so, yeah, like I said a couple times, exam FM, these writers have this strange obsession with using the quadratic formula. I don't really understand why that's very relevant to understanding and working in the insurance industry. But as I've said many times, who am I to question them, I guess. But anyway, so yeah, let's solve this. And you're going to use the quadratic formula, obviously. So let's bring all this stuff here to the right-hand side. And that way, when I multiply by I squared, I will not have a negative in front of the coefficient in front of the I squared. So subtract minus 50 from both sides. It's going, or rather, let's keep the 100 here. Plus 50 over I. And it's going to be minus 5 over I squared. Okay, so multiply everything by I squared. 100I squared plus 50I minus 5 equals 0. And you do quadratic formula, or rather divide by 5 everywhere. You get I is 0.0854. Okay. And I should really make clear that we're not going to consider I negative. So yeah, throwing out the negative solution, this is going to be your answer, 8.54%. So hopefully this was informative. Yeah, so this is actually the last of these new videos that I'm making. Loans and everything else is already up. Yeah, so I'm gonna in these ones videos that are already up, I revert back to the old put up PDF and go over things, but I don't think it makes enough of a difference to create new videos. But anyway, so long, take care. Yeah, good luck on today's quiz. Bye-bye.